If you haven't already done so, get phones put away, earbuds put away. If you've got a Chromebook out, shut it. You don't need it open for now. We're gonna talk about just a couple of things that, that relate to the work that we're doing with the simulation. This is part of a larger presentation, and I will give you more information about this stuff on Thursday when we have a little bit of time. But for today, what I want to get across is a couple of really key things. Number one, there's vocabulary here that's really critical. If you don't get the vocabulary, everything else is going to kind of be lost in translation. So knowing the vocabulary is going to be really critical. The second piece, yeah?
Are we taking notes?
You don't have to write this down. I'm going to just show you some stuff real quick. The second thing that I want you to see here is that there's two levels of skill that I want you to have. One is your ability to explain stuff. So that's this, how well can you characterize the diffusion of particles in a liquid solution? Characterize means describe. So I want you to be able to speak intelligently about this thing that we're going to talk about today called diffusion and a special subset of diffusion called osmosis. If you can't talk about it, then you don't really know it. So when I give you guys work to do, a lot of times the vocabulary is something that you need to like be able to access definitions, but you don't necessarily have to have them memorized. When you talk about something with knowledge and understanding, you have to know what the words mean. You can't look them up. You can't just be like going from a rote or memorized definition. You have to have a deep understanding of the concepts. And then the other two things that we're going to be thinking about are skills that have to do with making predictions. And those predictions involve being able to look at a scenario and say, oh, well, this solution is hypertonic relative to the cell. Therefore, something is going to happen. What's going to happen? Well, water's going to move this way or that way across the membrane. Emily, leave this in back. And then what I want to just really quickly run through is two definitions that are going to be really important. One is called diffusion, and diffusion is what happens when things spread out. We can talk about diffusion in a wide variety of contexts, but in this class we are typically going to be talking about things that diffuse in liquids. When things diffuse in liquids, they start kind of not spread out, and they end up spread out. That's it. So you can see in this image we have something that's not diffused, like there's more of it out here, and after some period of time it's all evenly spread out. And it always moves in the same direction. It always goes from where there's more of something to where there's less of something. That's actually a physical law. It's one of the laws of thermodynamics, that things will always become more spread out if they can. It's not gonna, things don't concentrate themselves. They don't get more concentrated unless something is making them get more concentrated. When we talk about diffusion in this class, we're often going to be talking about things diffusing from outside of a cell to the inside of a cell, or the other way around. So if, for example, you have a cell, and there's a lot of oxygen in the blood around that cell, and there's not that much oxygen in the cell, then oxygen will move from the blood to the cell. It does it automatically. Nothing has to happen in order for that oxygen to move into the cell. If there's more of it in the blood, it will automatically move into the cell. That's diffusion. And then the other thing that I want to go over real quick, and again, we'll go over this in more detail on Thursday, but I just want you to have just enough information to work through the simulation today. The other thing that we're going to talk about is something called osmosis. And osmosis is what we call passive. It doesn't take energy for osmosis to happen. It feels like it should. But one of the things that I want you to figure out today using the simulation is, why is it that this process happens without any energy? Why do we not have to force this to happen? Because you're going to see there's some weird things that can result because of osmosis. Osmosis is diffusion, but it's diffusion of water. So just like anything else can spread out, will spread out if it can, water will spread out if it can. And in this case, if we have water that could potentially spread out, and there's a semi-permeable membrane that separates water that could spread out from water that could be spread outable, then water will actually move across that membrane, and that's called osmosis. Osmosis happens when water moves from one side of a semi-permeable membrane to the other side, and in doing so, spreads out. And the reason that this happens is because everything has a tendency to spread out. Everything would spread out if it could. But if you have a semi-permeable membrane, you might have a situation where you've got molecules on one side of it that are too big to get through the membrane. They would spread out if they could, but they can't get through the membrane. So they'll spread out on the side that they're on, but that's as far as they can get. With osmosis, what ends up happening is you have pure water on one side of a membrane, and water with some stuff in it on the other side of the membrane. Then the water on the pure side of the membrane can spread out, and it does. Just like anything else. If you look at this image, you can see there's like more of these blue dots on the left-hand side of the membrane and fewer of these blue dots on the right-hand side of the membrane. So the water can and will spread out. And there's a couple of really interesting things that happens because of that. One is that there ends up being pressure. There will actually be a pushing force on this side of the membrane. If we were to look at an actual physical membrane, in an actual physical setup like this, what we would see is the membrane would curve. The membrane would actually be bent like this because the water would be pushing on it in this direction as it forces its way through. The other thing that can happen is as that pressure equalizes, you can end up with a solution, a liquid, rising up on one side of a membrane. So if we started with this situation and kind of just let it sit, eventually we'd end up with more liquid, more water on that side. And I have an animation that I don't know if this is gonna work, I'm gonna try to show you, oops, it's not it. I'm gonna try to show you, if it works, great, if it doesn't, it's not the end of the world, yeah. So, wait, okay, hang on, hold tight. It is working, it's just that I need to close this. All right, so here we have the situation that I just described where we've got pure water on one side of a semi-permeable membrane and salt water on the other side. The salt can't diffuse, it can't spread out because it can't move through the membrane. The water can spread out, so it moves from where there's more water, where it's pure water, to where there's less water, where there's salt. And you can see visually what's happening is that we're ending up with a higher amount of liquid on this side. And that actually happens in real life. It's called osmotic pressure. And it's a real thing. And in fact, osmotic pressure is really important for biological organisms because that's how we end up moving water in and out of cells, and that provides structure. We see it most with plants. If you don't water a plant, after a while it starts to wilt. That's because the water pressure in the plant is too low. So osmotic pressure is a really critical part of the structure of organisms. What I'm going to ask you to do now, and we're in good shape, we've got just a few more minutes before my meeting starts. So what I'm going to ask you to do is pop open your Chromebook and go back to the document, the assignment that we were working on the other day with the simulation. And I'm going to walk you through a few of the definitions and the first couple of data collections. I'm going to walk you through the first couple of data collection steps just so everybody is in the same place And everybody knows what the data collection should look like. So first of all, probably you discovered on your own that a solution is generally a mixture of a liquid and something else. That's not universally true. Solutions can be gas, we can have gaseous solutions, we can have aqueous solutions. Sometimes we mix two liquids together. But in biology, typically we think of a solution as a liquid, like water, with other stuff mixed into it. And in fact, in biology, almost always the solution is an aqueous, water-based solution, which means the solvent, which is the liquid part of a solution, is usually water. Not always. Definitely in chemistry that's not true. In chemistry you're going to use solvents like acetone. We can use rubbing alcohol as a solvent. There's all sorts of solvents that we can use. In biology, pretty much when you're talking about a solvent, you're talking about water. Yeah. Well, so you should have, you can keep your own words if you like them. You're welcome to grab mine if it's helpful. The solute is the stuff that's dissolved in a solution. And that can be anything. There isn't any usual in biology when it comes to a solute. Some of the examples of things that are dissolved in your body right now: oxygen, carbon dioxide, sodium, chloride, potassium. There's all sorts of sugars, like glucose is dissolved in your bloodstream right now. Your cell is full of solutes. Your cell has the same rough concentration as seawater when it comes to the stuff that's in it. So when we talk about solutes, it's not just one thing, it could be a whole bunch of things. The simulation that we're looking at, it has 3 different kinds of solutes and 1 solvent. The 3 solutes are just called like big, medium, and small. But in biology, those would generally correspond to actual things. Like a large solute might be something like a protein, something really big. A medium solute might be something like a sugar. And a small solute might be something like a sodium ion. Okay. So if we look at the simulation, and I'm going to kind of move back and forth between this, if we look at the simulation, what you'll see is these colors of the different substances indicate whether it's the solvent, which is the blue, and that's water, or small, medium, and large solutes. So if you look at the water is the blue dots. The solutes are the other dots. There's one red. I can't remember the colors. I'm sort of half colorblind. Red, yellow, and is that gray? Red, yellow, and gray. Okay, and then this membrane in our model is simulating a semi-permeable membrane, which means not everything can move through it. So only some of our molecules can get through that membrane. So we actually have to look to see what those are. So if I watch, I can see right now, it's really easy for me to see that the blue dots are moving back and forth. So the water can clearly move back and forth. And now I'm going to watch some of these smaller, the red ones. Oh, I just saw a red one go through, another red one, another red. The red ones can go through. Water can go through. The small solute can go through. What about the medium-sized solute? What about the yellow? Can that go through?
Yeah.
Ah, I just saw one. Okay, so the yellow can go through. And then, what about the large? No, you probably saw that the other day. Like, you can't rule it out because, like, if you just watch for a while and it doesn't go through, you don't know if it's because it can't or it just didn't. But it turns out the way this model is built, the large molecule cannot permeate the membrane. The medium can, the small can, and water can as well. Okay. Now we're going to do just a quick data collection, a round of data collection. Yeah, just so that you can see the kind of data that the simulation will give you and how to read that data. It gives data in graphical form, which is great for visualizing, not great for getting numbers, but we're going to be able to get numbers from that as well. So we're going to start by setting the large molecule on both sides to 2% and the other molecules to 0%. Why do we use percentages when we talk about these things? Shouldn't we just use numbers? The reason that we use percentages is the same reason that we talk about percentages when we talk about people and like people in a population. So let's say, for example, that you have about let's say 100 friends and acquaintances. If you have 100 friends and acquaintances at this high school, that means that out of the 1,000 students that go to this school, less than that, but just we'll make our math easy, you know our friends are acquainted with about 100 of them, right? So that's about 1 out of every 10. So that's about 10% of the students. So how likely is it that as you walk through the hallways, you're gonna see somebody you know? Pretty likely. But what if you knew 100 people in New York City? New York City has a population of like almost 20 million. If you know 100 people in New York City, you're never gonna see anybody that you know. If you know 100 people in Crescent Valley High School, you're gonna frequently see people that you know. If you know 100 people in Corvallis, it's gonna be hit or miss. Percentages matter more than numbers for a lot of these things. So when we talk about solutions, we care about percentages. If 2% of all the molecules on one side of our simulation is the large molecule, and there's no other molecules in there, then what percentage is water? If we have 2% of something, and the rest is water, yeah, it's 98%. So we can kind of figure this out by doing just a little bit of math. 2% is our starting amount of the large molecule. That must mean the other 98% is water. So let's set up our simulation. I'm going to set it up so that there's only large molecules and they're at a concentration of 2%, same on both sides, and then I'm going to run the simulation. And it says run it for 60 seconds.
Is the temperature?
What's that?
What about the temperature?
The temperature, it doesn't say to change the temperature to anything. So we can just leave it the way it is. And most of you probably saw yesterday that what the temperature does is it speeds things up, but it doesn't change the end result. So it's not that it doesn't have any effect, it's just that ultimately it doesn't have, it doesn't affect the final outcome, it just affects how quickly we get there. Yeah? Oh, is my meeting here? Are my meeting people here? Okay. All right, so let me just show you really quickly how you can get data from this graph. So if I click pause here, this is only 26 seconds in, not a minute. The key here is the data is shown with lines and colors. So gray, yellow, and red for our large, medium, and small molecules. Solid lines for the left-hand side of the beaker, dotted lines for the right-hand side of the beaker, and you can get numbers by just putting your mouse over the data. So if I want to see how things looked at the end of that 26-second period, I put my mouse over the very end, and these numbers are telling me the percentages. So it changed a little bit. On the right-hand side, I now have 2.03% large molecule, which means I now have 97.97% water. And on the left-hand side, I've got 1.97% large molecule, which means my water is going to be 98.03%. So that kind of data is what we're looking to have you guys collect. You, I think, should be able to get all the data collected, particularly if you work with a couple other people and kind of keep track of one or two things at the same time. And then what we're going to do on Thursday is we'll come back, I'll give you some more detailed information about diffusion and osmosis, and then we'll go back through and we'll interpret that data, and we'll be able to figure out why it is that sometimes we see something like this where there's hardly any change at all, other times we see big changes. And it all has to do with these ideas of diffusion and osmosis. Okay, I'm gonna stop the video.